Okay, so we are now on chapter 6 in the lecture, which is on the fundamentals of potentiometric titration, redox titration, and voltammetry. Okay, so as of now, I assume that you were able to discuss electrochem in your laboratory, no? Because knowledge in electrochem will actually help you understand this topic more, no? So I hope the laboratory instructor were able to do that. No? Pero if not, that's still okay. No? So it's still okay. But I hope na maturo din, ma-discuss din agad. Okay. So this is the topic outline for our session today. We will try to cover all of this and kaya naman yan. So let's start now. So we will discuss first about a basic concept of electrochemistry and electrochemical cell. Again, this will be discussed in depth in the laboratory. Okay. Then we will proceed with the Nernst equation and the solving for the equilibrium constant in redox reactions. And we have redox titrations, potentiometric titration, and voltammetry. Okay, so we'll try to cover all of them. Okay, so this is quite a lengthy topic. So, yan. So let's start now. So, electrochemistry is a field of science which deals with the conversion of chemical energy and electrical energy. No? So, one example of the application of electrochemistry would be our batteries. No? So, in our batteries, suppose you have your laptops or your cell phone devices with you. Uh, you know that you know that you can use these devices even though they are not plugged in the power socket, no, because of their batteries, no? So batteries are storage forms of electrical energy. So what actually is inside the battery are just chemicals, and those chemicals, depending on their concentration, will produce electricity. Okay, so another example would be this one. So this is a stack of coin with paper submerged in zinc. So if you combine zinc and copper coins, you can actually power an LED light. Okay, so this is the example of electrochemistry. So we are going to understand and how to utilize the conversion of chemical energy and electrical energy. Okay. So you may ask, is this related with my field? The answer is yes, no. Because in medical technology, you want to try to measure the amounts of particles in the body, okay, using some devices. No? So this is still related in our field, although my examples were batteries. Okay. So how can this be applied in your field? So one of the application of electrochemistry in your field is the use of glucometer. Okay. So in glucometer, let me zoom in. Okay. So this is the glucometer. It is used to measure the glucose level in the blood, especially if the person is diabetic. So to monitor blood sugar, we use this. Okay, so I actually have one, although nobody's diabetic at home. I just have one. Okay, so how this works? That you prick your finger. Okay, you prick your finger until the blood will come out, then that blood will be transferred to a very small well in this portion of the glucometer. Yeah, so this is the test strip. Then you place your blood on that small well in that test strip. Okay. Then what will happen is that you allow this device to work for about 5 seconds, and then later on it will give you the sugar level. Okay. So for example, the sugar level here is 5.7 millimole per liter or 57 millimole per deciliter, which is actually a very low blood sugar. Okay, so low sugar siya. Okay, so this is one application of electrochemistry. How? Okay, because what happens here is that when you place your blood in that well, okay, what happens is that this device actually measures how much voltage can be transmitted by the blood. We know that liquids can transmit they can transmit electricity, especially when they have ions in it. And that is what the glucose meter is doing. Okay. So we know that our blood consists of many compounds. One of them is glucose. And when you subject those molecules into an electric current, okay, there's some reaction happening in there. Okay. So depending on the and to the extent of the reaction, then it can measure the voltage, or it can measure the, yeah, it can measure the voltage of the uh, voltage passed through the blood. And soon as you know the voltage that is passed through the blood, you can now determine the concentration of the sugar. Okay. Okay, so again, how this works is that you place your sample, you allow the electricity to pass through that sample, and the device will measure how much electricity was transmitted by the sample. Okay, so depending on the voltage the that the sample transmitted, you can get your sugar levels. You can get the concentration. Okay, so this is one application of electrochemistry. So again, this is not just this is not just the typical anachem subject, but this is relatable in your field. No, so knowledge in electrochemistry would actually help you um, uh, it would actually help you understand devices like glucometer. Okay, and hopefully one day you will be able to create your own device. You can create a device that can measure the content of, let's say, urine, or let's say saliva. Okay, so it uses electrochem to do that. Okay, as of now, if I'm not mistaken, the way we do urinalysis is that we use spectrophotometry. So you place your urine sample, and then you add some chemicals onto it, and then a test strip will be added. And depending on the intensity of the color of the test strip, you can determine the concentration of the metabolites in the urine. Okay, but if it is also possible to do something like a glucose meter for urinalysis. No? So hopefully, one of you someday will be able to do that. Okay, and I hope you get patented. You will earn lots of money when you have patent. Okay. So another example of the application of electrochemistry is this, no, the pH meter. So what we have here is in the pH meter is that you have the probe here. Okay. So this is the pH meter. You have this monitor that will give you the readout. Then you have this probe here. So how to use the pH meter is you submerge the probe in the solution, and then you allow the device to read uh, amount of concentration, the amount of hydronium ion in the solution, and that will give you the pH. Okay. How is it done is similar with the glucose meter. Okay. So in reality, this device will actually pass through certain electric potential in the solution. Okay. Because there are ions in the solution, then electricity can be passed through it. Okay. Depending on the amount of depending on the amount of the electricity that can be passed through this solution, it can measure the concentration of hydronium ion, and it can give you the pH of the solution. Okay, so basically electrochemistry relates the amount of voltage that can be passed through in a system with your concentration. It relates the voltage with the concentration of your chemical species. Okay. And with that knowledge, we can do lots of stuff in electrochem. We can have lots of application in medical field or in pure sciences. Okay. And these two are just some examples of those applications. Okay. So if you look up in the internet, the application of electrochem in medtech, in medicine, there's lots of them. Okay. However, for simplicity, I use this two because I'm sure some of you may be familiar with glucose meters, especially if you have diabetic relatives. more chances that you actually saw this working. Okay, so that's why I placed this as an example. Okay, so anyway, so my point is that electrochemistry is related to your field. Okay, so understanding this would actually help you um, appreciate all these devices we use to measure chemicals in our systems. Okay, for example, in our body. Okay, so this is important. Okay, but again, um, that is just an application, so you still need to understand the fundamental theory of this subject, okay, for you to know how they are made. Okay, so let's go back to batteries for now. Okay, so let's go back to batteries now. So if you have this setup, so this is actually my experiment with my students last 2019. Okay, so I handled engineering class and we made batteries on that subject. Okay, so that's chemistry for engineers. Okay, so in that subject, we were able to create electrochemical cell. Okay, so what is an electrochemical cell? It is a system which consists of an electrodes, which consists of electrodes dipped into the solution. Okay, and depending on the chemicals you place in the solution, they could either give off or take in electricity. Okay, so this is one example here. So this is our metal electrode. So on the left you have the magnesium bar. I mean the magnesium ribbon. Okay. So this is the magnesium ribbon, and on the right you have the copper wire. Okay. The magnesium ribbon is submerged into magnesium ions. Okay. So this is magnesium sulfate. Okay. And on the right side I have here copper sulfate. And then in between I have this salt bridge. Okay. So the salt bridge is used to maintain electrical neutrality. Okay, so this will be discussed in the lab anyway. So yeah, so this is my set. This is our setup. Okay, so we have magnesium solution. We have the metal, the magnesium electrode. Then we have the copper solution and the copper electrode here. So if you connect that solutions in a voltmeter, there will be a potential reading. So there will be a voltage reading. Okay. So apparently this gives off around 1.5 volts electricity. Okay. So by adjusting the concentration of the ions in here, you can increase or decrease the voltage reading. Okay. So that means that this topic is not just a concept. No, rather it can be done in the laboratory. Okay, so you can do this in the lab. Okay, and this is how our battery works in reality. Okay, so our battery, it consists of two systems. It consists of an anode and a cathode, and then depending on the amounts of the ions present in there, you can create you can produce electricity that can power your devices. Okay, so if the setup produces voltage, for example this one on the right side, it produces voltage which is positive 1.5 volts. Okay, if it produces voltage, we call that voltaic or galvanic cell. Okay, so voltaic or galvanic cells are electrochemical cells that produces electricity. Okay, however, another setup is called the electrolytic cell, wherein the reaction needs electricity for so the reaction needs electricity for it to proceed. Okay, so this is one example. These are two examples here on the left. Okay, so let me just explain what's happening in here. So on the left side, on the leftmost side, we have here water solution with ions. Okay, and then I have two pencils here. Okay, so pencils can actually serve as electrodes. Okay, the carbon inside the pencil can actually allow electricity to pass through. Okay, so that is what we did. We connected the pencils in a battery, and then what happened next is that a reaction happened. Okay, so water actually broke down into two components. Okay, so the reaction that happened on the left side is this. Um, okay, so this is the electrolysis of water to produce hydrogen gas and the oxygen gas. In one electrode, the hydrogen gas will form. On the other electrode, the oxygen gas will form. Okay. And this technology is used by scientists, especially those who travel in outer space, no? So that they can have oxygen to breathe. No? So this is actually what they do. Okay, so yeah, so this is what that they actually do to get oxygen. Okay, I think this technology was used in Apollo mission. Yeah, the one that went to the moon. Okay, so they use this technology, the electrolysis of water, to get oxygen that they can breathe, and as well hydrogen gas, which can be used as their fuel. Okay, so if you may ask that since we produce hydrogen gas, so are the gases flammable? And the answer is yes. Okay, what we actually did here during the experiment is that we allowed this setup to run over a short period of time, maybe around 2 hours. Okay. So once we were able to set this up, we allowed the reaction to happen in 2 hours, and then after we collected lots of gas, we actually ignited them. And yeah, it ignited. Okay. So the hydrogen gas combusted no, when we subjected it to fire. Okay. So that means this reaction is true. This topic is really true. You can actually replicate this at home, provided that you have to have two pencils. Okay. Shape of the ends of the pencil. Okay, and then you should have 9 volts battery. Connect the battery um, to the carbon end of the pencil, and then watch that observe that this reaction will happen. Okay, you can do this at home. Okay, another application of electrolytic cell is this one, the copper plating. Okay, so in this experiment, this is actually my key to my dorm. Okay, when I was teaching face to face, I live in a dormitory pa. Okay, so this is my key to the dorm, and then I have here the copper solution, and then I have copper metal here. Okay, so what happened here is this: when you allowed electricity to pass through this setup, what happens is that the copper ions will be reduced onto the metal surface. Okay, so the copper ions in the solution will be reduced on the metal surface, and then we can call this metal the copper coated metal. Okay, so we have a copper coated key. Okay, so we are familiar with copper coated materials at home, especially in the kitchen. So there are copper coated um, cookwares, right? Okay. So how were they able to do that? Okay. So basically, you just prepare your cookware, and then you submerge it into copper sulfate solution, and then you allow electricity to pass through it. Okay. As electricity passes through the solution and the metal that you want to coat, okay, what happens is that the ions will be reduced on the surface of the metal. Okay, so from copper 2 plus, it will now become copper metal. Okay, so that is how electrolysis is done. Okay, that's how copper plating is done. Okay, also in jewelries, you are familiar with gold plated or silver plated jewelries. How are they able to do that? Same concept lang. Okay, so you just submerge your metals, your jewelries, in a solution of gold or copper or silver. Okay, so you just submerge your jewelries in those solution, and then allow electricity to pass through, and then what will happen is that the ions will be reduced onto the surface of your jewelry. So uh, you will have gold plated jewelries or silver plated jewelries. Okay, so yeah. So in galvanic cells, oxidation happens on the anode, and and reduction happens in the cathode. Okay, so my mnemonic for this one is the oxan, red cat. So this is the mnemonic device that I use to memorize this. Okay, so oxidation happens on the anode, so that is the oxan. Oxidation on the anode, and the reduction will happen on the cathode, the red cat. Okay, so by this time you should know what's oxidation or what's reduction. Okay, so oxidation is the process wherein the atom will lose electrons. Okay, that means that its oxidation number will increase over time. Okay, and reduction are reactions wherein the oxidation number of atoms decreases. Okay, so this is the reaction wherein your ions becomes solids. Okay, so just like what we did here. Okay, so that happened here is the reduction of copper onto the surface of your metal. So that is described by reduction reaction. Okay, so again, for you to memorize this, you have oxidation on the anode, reduction on the cathode. Okay, and the salt bridge is the one that maintains electrical neutrality in the setup. Okay, so for example, this is my oxidation, this is my reduction. So this is the anode, this is the cathode. In between them, I have to place my salt bridge. Okay, so the salt bridge will maintain the balance in the um, charges of the ions. Okay, because if the charge of the ions builds up, then the reaction will stop. Okay, so without the salt bridge, this will not produce any voltage. Okay, so this is how a galvanic cell looks like in theory, and this is how it looks like in reality. Okay, so they have similar features, no? So on the left side you have your anode, on the right side you have your cathode. Okay, so you have your anode on the left, and then you have your cathode on the right side. Okay, so again, on the anode, what happens here is that oxidation reaction will occur, and on the cathode we have the reduction reaction. Okay, so again, when oxidation process happens, what happens here is that your particles or your atoms becomes more positively charged. Okay, so for example, we have copper metal here. When it is oxidized, it turns into copper 2 plus. Okay, and during the process, it produces two electrons. Okay, so it produces two electrons, and I assume by this time you know how to balance redox reactions. If not, you can watch my lecture videos, but that's in Tagalog now. Okay, so yeah. Anyway, so I assume you know how to balance redox now. But if not, you can watch my lab videos on section 2. Yeah. Okay. We discussed balancing last yesterday. Okay. So anyway, so on the oxidation reaction, we have the metal turning into ions. Okay. So this is what happens in the oxidation. It increases its oxidation number, and during the process, electrons are released. Okay. So the released electron will travel through the electrode, passing through the voltmeter or your device. Okay. For example, LED light. You can use LED light to replace the voltmeter. Okay, and that electron will travel to the right. Okay, so it will travel to the reduction or to the cathode, wherein the reduction reaction will occur. So what will happen here is that uh, your metal your metal oxidation number will decrease. So for example, we have silver ion here. It will be reduced to silver metal. Okay, so over time, the copper on this part of the solution the copper metal uh, will decrease in amount because they are being converted into ions, and on the right side, your silver electrode will increase in mass because the ions are being deposited on the electrode. Okay. So again, quick summary. This is how the electrolytic cell, this is how the voltaic cell will look like. You have the anode and then you have the cathode. On the anode, you have your oxidation. And on this part of the container, you have your metals losing electrons to produce ions. That electron will pass through this metal, okay, okay, to the right side. Okay, so it will pass through this metal until it reaches the cathode. Okay, and on the cathode, that supplied electron is used to reduce the metal ions into metal. Okay, so that's that's voltaic cell. So if you want to determine the cell potential of the of the voltaic cell, you can use this equation. So that's E cell equals E cathode minus E anode. Okay. Your lab prof may use E right minus E left. Okay. But I prefer to use this one because this is consistent with our labels. No? We know that cathode reactions are reduction reactions, anode reactions are oxidation reactions. Okay. So your lab prof may use this E right minus E left, but this is just the same as this one. Because on the right side, you have your cathode, okay? So that's why it's sometimes called E right, okay? Because you have your cathode on the right side, and then you have your anode on the left, okay? So that's E right minus E left, or E cathode minus E anode, okay? So this equation is used to determine the cell potential of a certain chemical reaction. Okay, so meaning you can determine the voltage this reaction will produce. Okay, so all you have to do is that, for example, we have this cell notation here. How to interpret the cell notation. So I hope this was discussed in the lab, but let me go through this very quick. Okay. So this is the cell notation. On the left side of the cell notation, you have your anode reaction. Then on the right side, you have your cathode reaction. Okay. So the left side of the cell notation tells you that copper is converted to copper 2 plus. Okay. So that is the reaction on the left. And on the right side, you have your silver ion converting into silver. So you can combine those equations to create the equation Cu plus Ag plus producing Cu2 plus and Ag. Balancing this will give us this two coefficient for silver and silver ion. Okay. So again, I hope that this was discussed in the lab. Okay, but if not, then you can, you can you can watch my videos on this. Okay. So that is how you interpret cell notations. The reactions on the left are the anode reactions, and on the right you have your cathode reaction. Okay. So since we know that on the left is your anode, so we will determine what is the voltage produced by this reaction. What is the cell potential produced by that? Okay. So for you to know the potential produced by that reaction, you have to refer to the standard reduction potential table, the SRP table. Okay. So let's look for ions, uh, for the copper 2 plus ion and copper metal in this table. Okay. So all you have to do is to look for those ions in the table. Hmm, asan kaya? Okay. Wait lang. Where is that? Okay, so this is the copper 2 plus copper metal reaction here. Again, it doesn't matter if the reaction is reverse or not. Okay. So if you look at the table, copper metal, the reaction is written as this. Okay. But in our system, the reaction is written as this. Okay. So it doesn't matter actually whether that's reversed or not. Okay. So all you have to do is to just look at the table if it contains copper 2 plus and copper. Okay, so you just look up this table. For example, you have copper 2 plus here, and then we have copper metal here. So you use that cell potential. Okay, so don't mind whether that is reversed or not. Okay, so what we are after is the cell potential here, which is 0.34. Okay, so the E anode will be 0.34 volts. And then for the cathode, it's silver ion. Okay, so let's look at this table. Silver. Okay, so this is the silver ion silver reaction. Okay, so the cell potential of that reaction is 0.80 volts. Okay, E cathode is 0.80 volts. Okay, so all you have to do, since you know the cell potentials that's given on this table, you have to plug it here. Okay, plug that into our equation. E naught cell equals, for cathode, that's 0.80 volts. For the anode, that's 0.34 volts. Okay, so what's the difference? 0.8 minus 0.34. Okay, so the cell potential is 0.46 volts. So that means this reaction will produce 0.46 volts. Okay, and because it is positive, we can say that this is galvanic. Okay, galvanic because the cell potential is positive. Okay, it means it can generate electricity. Okay, you can connect this reaction and it will produce electricity. Okay, so if we have non-standard systems, okay, so what's the difference between standard and non-standard potentials? Okay, so the only difference is this: if you have standard potentials, we assume that the concentration is equal to 1 molar and the pressure of gases is equal to 1 atm. Okay, so this is what we assume if we have standard cell potential. This solution is 1 molar in concentration. This solution is 1 molar also in concentration. However, if those concentrations or pressure is not equal to 1 molar or 1 atm, then we have non-standard systems. Okay? So again, non-standard systems are reactions which do not have concentrations equal to 1 molar or 1 atm. Okay, so that is the non-standard cell potential. So for you to determine the E cell, you have to use the Nernst equation. So the Nernst equation tells you the relationship of the concentration of your ions in the reaction. Okay, so the Nernst equation is written as E cell equals E naught cell minus 0.0592 over mole of electrons logarithm of Q. What is Q? That's reaction quotient. Okay. So before you use this, you have to balance the equation first. Okay, so you have to write the cell potential. I mean the cell notation. You have to write this cell notation into a chemical equation first. Okay. So again, this is your anode, and this one is your cathode. Okay. Remember that in the anode we have copper converting into copper 2 plus. So that's the reaction in the anode. And in the cathode, you have your silver converted into silver. I mean, silver ion converted into silver metal. So if you balance the equation first, you will see that this will need 2 electrons. This will need 1 electron. Okay. I hope you know how to balance this. But again, if you don't know yet, you can watch my lab videos on this. Okay, and that was uploaded in YouTube last night. Okay. So before you combine the two equation, you must make sure that the electrons must be equal. So you get their least common multiple, which is 2 times 1. So that's 2. So that means this equation should also have 2 electrons. Okay. So to do that, you multiply this side of the equation by 2. Okay. So you multiply the equation by 2. So now this reaction will have 2 electrons, and that will be the same as this one. So if we combine the two reactions, that will become, what's your reactants? So 2 electron, 2 Ag plus, and copper. And your reactants will be copper 2 plus, 2 electrons, and 2 Ag. Since we have electrons on left, on the right, and on the right side, you can cancel them out. Okay. So the reaction can be written as 2 Ag plus Cu Cu2 plus 2 Ag. Okay. So that is our reaction. Okay. So again, what I did is just I balanced the equation. Okay. So let me erase this again. Let me rewrite that here. So we have copper plus 2 Ag plus producing copper 2 plus Ag. Okay. So now we have our balance equation. Then we can use the Nernst equation. Okay. So we have E cell equals E naught cell minus 0.0592 over mole of electron. What is the mole of electron that we had earlier? That's 2, right? Okay. So we knew that we have 2 electrons transferred in this reaction. Okay. So the one that we canceled earlier. Okay. So that's the moles of electron, and that is what we are going to use here. Okay, so the mole of electron is 2 according to our balancing. Okay, so you plug it there in the denominator. Log Q. Okay, so we have the logarithm of the Q. Again, what is Q? That's reaction quotient. And that's similar with the equilibrium constant. Okay, so all you have to do is to uh, write the concentration of the products and the reactants. Okay. So on the products, okay, so we have copper 2 plus and silver metal. Okay, so again, metals or solids are not written on the K or Q. Okay, so you should not write any metals on this. Okay, so that means I'm just going to write copper 2 plus here on the numerator. Again, metals are not ought to be written in here. Okay. So you should not write this down here. Only the ion form or the gas form. Okay. Then on the left side, we have the reactants, which should be placed in the denominator. So again, metal, copper metal should not be written because it is solid. But this silver ion can be written. Okay. So we can write that as Ag plus squared. Okay. Take note that the coefficients are made exponents here. Okay. So the 2 will be the exponent for this one. Now, what's the concentration of copper? Concentration of copper, according to the equation, is 0.02. Okay. And then for silver ion, that's 0.02 squared. Okay. So let's plug this into our equation, knowing that copper is 0.02 and silver ion is 0.02 squared. Okay. So let me use my calculator here. So you will know what to type. Okay. What's the E naught cell? By the way, let's go back here. What's this now? This is the standard cell potential, and the standard cell potential can be calculated using this table. Okay. So this E naught cell, the circle on the top is called naught. Okay, NOUGHT. Okay, so that's pronounced not. Okay, so E naught cell is the standard cell potential, which we just solved earlier. Okay, so we just knew earlier that the E naught cell is 0.46 volts. And again, this can be obtained from the table. Okay, so just look for the potential of the anode and the cathode, then subtract them. Okay, then you will get this. Okay, so you can use the table. Okay, to get that. Again, this is 0.46 volts according to our previous calculation. Okay, so anyway, solving for that, we have 0.46 minus fraction bar 0.0592 over 2 logarithm of, on the numerator, we have 0.02 for the copper ion. And then on the denominator, I have 0.02 squared for the silver ion. Okay, so again, this is how the equation will look like. This is the E naught cell minus 0.0592 over mole of electron, which is 2, logarithm of Q, which is the product over the reactant ion concentration. Okay, and then you press equal sign. This is now the new potential, 0.40. Okay, let's round it. Let's round this off. 0.46. For 0.41 rather. Okay. So our cell potential is 0.41. Okay. So that means by changing the concentration, you can determine the different. You can, by changing the concentration, you can determine the new cell potential. Okay. So that means this is what our pH meter and glucometer is doing. So what they actually solve is the E cell. Okay, the E naught cell is already programmed in the software of that of those devices. Okay, so they know what's the E naught cell already, and what they are just looking for is the E cell. Okay, so they will determine the voltage transmitted by the solution. Okay, so by just looking at the difference of the two, the standard and the non-standard cell potential, they can calculate this. Okay, so what we did is that from the concentrations we get the E cell, but our instruments, especially pH meter, what they do is that they solve for the E cell. They determine the E cell, okay, of the solution. And so that means they will pass through some electricity on the solution. Then by knowing that, they can use that info to solve for the concentration. Okay, so they will derive some equations that will give us the concentration and in turn the pH of the solution. Okay, so that is how our glucose meter and pH meter works. They just know the E cell. Okay, and then by knowing E cell, they use this equation, then they look for the concentration of the ions. Okay, so they do the reverse of what we did. Okay, so for you to work, for you to practice, I want you to work on this. Okay, so the reaction on the left side is written as this one. Mm, so this is the anode reaction. Um, wait. Okay, so this is the anode reaction. So I want you to balance the electrons. Okay, and for the cathode, that will be this one. So the ion in HCl is H plus. Okay, so that's just H plus turning into H2. Okay, so this is the anode reaction. You have the silver with chloride ion producing silver chloride precipitate. Then you have your hydronium ion converting into hydrogen gas in the cathode. Okay. So in the lecture, in the laboratory, balancing this will be discussed in depth. Okay, so I hope you were able to do that. Okay. Okay, so the cell potential can be obtained on this table. Okay, so again, it doesn't matter whether the reaction is reversed or not. Okay, just look for the E cell. Okay, so just look for the E cell there. Then you can solve for this. And then after you write the equation, you can now write the Q. Okay, so plug in the ions that can be written on the Q. And then plug in their concentration. Okay, so by the way, the concentration of Cl here, the concentration of H and the Cl is 0.022. Okay, so that means the Cl concentration is 0.02 molar, and then the H plus concentration is 0.02 molar, and hydrogen gas is 0.8 atm. Okay. Again, hydrogen gas can be written on the Q. Okay. So before in chemical equilibrium, we have separate equations for gases and ions, right? Okay, so we have the Kp and the Kc, but for Q, it doesn't matter whether that they are gas or whether they are gas or ion. Okay, so for Q, it doesn't matter whether they are ion or gas form. So that means you can combine the pressure here. Okay, you can combine the pressure here together with the ion concentration. Okay, so I want you to work on this. I will upload the solutions for the questions in this slide by weekends. Okay, so I will upload the solution so you can work on those problems. Okay, and that will be included on the quiz. Okay, so yeah. So since we now know how to solve for the E cell, you can actually determine the delta G or the free energy change. Okay. So what is free energy change? So this is just the energy involved in the reaction. If this is positive, then the reaction is said to be spontaneous. Spontaneous. I don't have any space. Let me move it here. So again, if delta G is positive, it means it is. I mean, it's non-spontaneous. Sorry for that. Spontaneous. And if that is negative, this is spontaneous. Okay. So if our delta G is spontaneous, it should have negative value. Okay. So, so you plug in your E cell, and if you got negative delta G value, then that is non-spontaneous. That means, that's spontaneous. That means the reaction will happen instantly. Okay. So the reaction will happen instantly if the delta G is negative. But if the delta G is positive, that is non-spontaneous. That means the reaction will not happen instantly. Okay. For voltaic cells, delta G is negative. Okay. So that's why we said that voltaic cell spontaneously produces electricity because their delta G is negative. Okay. So by law of thermodynamics, if you have negative L delta G, then the reaction will proceed as usual, okay? But if your delta G is positive, this is non-spontaneous. One example of this is the electrolytic cell, okay? So if you place your metal onto the copper solution, the coppers will not instantly be deposited onto the metal surface, okay? But for you to do that, you have to apply electricity, okay? So applying electricity in the solution is non-spontaneous, okay? You have to have a driving force to do that, okay? So that's why electrolytic cell is a non-spontaneous process because you have to add electricity for that to happen. But for voltaic cell, the production of energy um, is instant, okay? For example, in our batteries, no, the draining of our batteries is spontaneous process. It produces electricity. So our batteries will be consumed over time because the delta G is negative. But if you want to reverse the reaction, you plug it into the power socket. Okay, so when you plug in your device into the power socket, then the battery percentage will increase because you are doing a non-spontaneous process. Okay, when you are charging up your batteries, then the delta G is positive. But if you are discharging it, no, then the delta G is negative. Okay, so what is the relation of this in our topic? So if you are asked to solve for the equilibrium constant K, if you want to solve for the equilibrium constant, you can use this equation. In thermodynamics, we know that delta G equals negative NFE. And in thermodynamics also, we know that it is also equal to RT ln K. Okay, so that means, let me rewrite this. So delta G is equal to this, negative NF is E naught cell, and that is also negative RT ln K. So if you want to solve for the equilibrium constant, then you can just plug in the info that is necessary for this one. N is the mole of electron. Okay, when you balance the reaction, you can get the mole of electrons. F is the Faraday's constant. This is the Faraday's constant. And this has a value of 96,480, I think. Let me verify if my value is correct. Let me verify if my value is correct. Wait lang. Faraday is constant. Okay, so 96480. Yeah. 96485 na lang. Okay. So 96485, that's the Faraday's constant. Okay. Constant. 96485. Okay. So yeah. So close. No? Okay. So anyway, so that's 96485. That's a constant we use in electrostatics in physics. And the E naught cell, oh, you know how to solve for this? So it could be standard cell potential or non-standard cell potential. Okay. So you know how to solve that with our previous exercises earlier. What's R? This is the gas constant, which is 8.314 joule per mole Kelvin. T is the temperature in Kelvin. And K is the equilibrium constant. Okay, so we need that. We need this equation to solve for the equilibrium constant given a cell potential. Okay, so let's try this problem. So find the equilibrium constant for the reaction below. Okay, so one way to solve for equilibrium constant is using the Nernst equation, but that is quite a lengthy process, so I won't use that anymore. But again, that will give you the same answer anyway. Okay, so I will not use the Nernst equation. In my previous section, in section 1, I taught the Nernst equation. However, it took us quite a while no, to get the correct answer. So I will just give you the shortcut anyway. Okay, so I'll just inform them that they can also use this equation. Okay, so this is the long method, the use of Nernst equation. But again, I don't want to use that anymore. Okay, so I will use the delta G. Okay, so according to our equation earlier, um, negative NFE cell is equal to negative RT ln K. So actually, you can cancel out the negatives. Okay, you can convert that into positives. So let's write it here. NFE naught cell equals RT ln K. So since we are solving for K, okay, so we just need to do some algebra. You divide both sides by RT, okay, so we will get negative, NFE over RT. That's equal to ln K. Now, how will you get K out of the natural log function? If you have a log function, if you want to get the K, then we use the anti-logarithm. Okay, you make them the exponents of 10, right? And we know that 10 and the logarithm will cancel, giving us k. Okay. But in terms of ln, instead of using 10, we will use the Euler's number. The Euler's number e, which is 2.71 something. Okay. So again, logarithm and natural log or ln are similar, but instead of using 10 for ln, we use the e, the Euler's number. And this is actually in your calculator anyway. Okay. So to remove the k from the ln, we use the Euler's number as our base. Okay. So take note of that. That is discussed in your high school algebra anyway. Okay. So we have e raised to ln k equals e raised to nf e naught cell over rt. So again, e and ln can cancel out, giving us the equilibrium constant k, nf e naught cell over rt. Now, since we know the equation already in solving for the k, then we should also know the constants that we have to plug in. Okay. So what is the moles of electron? If you balance this equation, you will get that the moles of electron is equal to 2. Okay. So the mole of electron in this equation is equal to 2. Right. So I will leave that to you for to solve. Okay. But by just simple inspection, the mole of electron is 2. Okay. The E naught cell, have we calculated for the E naught cell? I think we were able to solve for that. No. Copper, copper 2 plus silver ion, silver. Okay, so this is the E naught cell. So it's still 0.46. Okay. So we solved for that earlier. So mole electron is 2. The E naught cell is calculated earlier. So this 0.46 volts. The Faraday's constant is 96,485. Okay. The unit is coulombs. Yeah. Yeah. C. Coulombs or volts per mole. But again, I will not write down the units. Okay. R is 8.314 joule per mole Kelvin, and then the T is if the temperature is not stated, then you just use 25 degrees Celsius. Again, if the temperature is not stated, use 25 degrees Celsius or 298.15 Kelvin. Okay, so with all those info, we can plug them into our equation so we can solve for the equilibrium constant which is needed in this problem. Okay, so we have N which is 2, F which is 96,485, E naught cell is 0.46. Again, I'm not going to write the units anymore because we assume that they will cancel out. We are assuming that they will cancel out. R is 8.314 and T is 298.15. Okay, so let's plug this into our calculator and let's see what's K. By the way, apologies if my voice is quite quite unclear because um, apparently my throat is quite abused. No, medyo abused na yung throat ko. I've been teaching for 6 days a week kasi. So, my throat wasn't able to catch up with that workload. Okay, so, yeah. Anyway, so E raised to. Okay, so again, how to get that in your calculator. So this, if you can see E, then you have a box on the top. That's what you're going to use. Shift and ln, you will get this. Okay, so just type the fraction bar. Then on the numerator, we have 2 times 96485 times 0.46 volts. And on the denominator, we have 8.314 times 2.9, 298.15. Okay, so this is NFE RT. When you press equal sign, this is our answer. 3.56 times 10 raised to 15, or 3.6 times 10 raised to 15. If you look at your textbook, the answer there is written as 4 times 10 raised to 15. This is in your textbook, okay? But we can use this answer anyway, okay? So what can we notice is that the K is very big, right? So the K is so high. And we know if our K is greater than 1, then the reaction will proceed to the right, meaning the reaction is spontaneous. Okay? So we just solved that the K is a very big number. That's times 10 raised to 15. So that means this reaction will really happen. Okay? So this is how you solve for the equilibrium constant given the cell potential. Okay? So however, if you don't have any, if the reaction is non-standard, you can use the Nernst equation. Okay, so I just showed you how to use the Nernst equation earlier. Okay, so this can be calculated using the table. Then you plug in the necessary info. You should write the correct equation. Then you will get the E cell. Okay, so I want you to work on this problem. I will give you the cell potential for the reactions. Okay, that's 2Fe3 plus. This was not written on the table, so that's why I'm giving this to you. So 0.536 volts. Okay, so there you go. So these are the standard. Uh, these are the values you need to use when solving for the E naught cell. Okay. Okay. So look at the equation here. So Fe3 plus to Fe2 plus. So this is reduction. Okay. So that means this is your cathode. Okay. This is your reduction. Then you have I minus to I3 plus. Again, it doesn't matter if the reaction here is reversed on the table. This is your anode. Okay. So you now know how to solve for the E naught cell. That is E naught cathode minus E naught anode. Okay. Just plug in this value, then you will get the E naught cell. Then use the K equation we just derived earlier to get the K, the equilibrium constant. So I will leave this to you. I will leave that to you for you to work on. But again, I will upload the answers to everything that we just computed. Okay, so that you will have a reviewer for the upcoming quiz 6. Okay. So this topic will only have one quiz anyway. So electrochemistry can be also used in titration. Okay, so we can also do titrations with electrochemistry. However, remember that for acids and bases, our titration curves look like this. Okay, so you have the pH and then the volume of titrant below. Okay, and then it will have a graph looking like this, or reverse, or anything else. Okay, so this is the acid base curve. Okay, so the vertical axis is in term of pH. But for electrochemistry, or for redox titration, the graph will look like this. Instead of using pH as the vertical axis, we use the E cell as the vertical axis. Okay, and the horizontal axis is still the volume of the titrant. Okay, so it will still have the same appearance. Okay, but again, take note that instead of having the pH as our vertical axis, we will use E cell as the vertical axis. Okay, so since we can do titrations here, then that means we can solve for the E cell of our solutions. Okay, so depending on which stage are you in, depending on which stage you are in, you can solve for the E cell of the system. Okay, So you can solve for the individual points here, and these are the equations to be used, similar with titration. Okay. So depending on the composition of the solution, there is a corresponding E cell, just like acid-base titration. Okay. So for initial, there is no equation. Okay. So you cannot solve for the E cell of the initial. Okay. So yeah, that's so yeah, that's the case. No? You cannot solve for the E cell of the initial stage. Why? Because there is no redox reaction happening. Okay, if there is no redox reaction happening, then there will be no E cell reading. Right. So that means we don't have any equation to describe the initial stage. So we will just skip that. We will proceed with the other stages anyway. So we will have the pre-equivalence, equivalence, and the post-equivalence point. At pre-equivalence, mostly your solution is composed of analyte. So the equation to be used is the Nernst equation for the analyte. Okay, so this is the Nernst equation for the analyte. Okay, so you need to use the Nernst equation for the analyte. Okay, so by the way, this Q is the reduction reaction of analyte. Okay, so we will use the reduction reaction of analyte because we are describing the Nernst equation for the analyte only. Okay, so the E naught cell of the analyte can be determined using the table. Okay, so E naught cell of the analyte is not the E cell. Okay, it is not the E cell. It is whatever is on the table. No? Okay. So I will upload the worksheet that will use this in a problem. Okay. So at equivalence point, we assume that all ions are equivalent. Okay. So this is the equation that we need to be used. 2E system. So what is this? Okay. So 2E system is just the added potential of the analyte and the potential of the titrant. And this is the equation to be used. 2E system equals A, E analyte plus B, E titrant. Okay, where A and B are the moles of the analyte and the titrant. Okay, and the moles are given in a balanced equation anyway. So for the post-equivalence point, this is the equation. So mostly our solution is composed of titrant. Therefore, we need to use the Nernst equation for titrant. And again, the Q is the reduction reaction of titrant. So that is the reduction reaction of titrant. Okay. So anyway, Q is already given here. So this is the corresponding equation to get the Q. So that's MAVA, MTVT. So take note that MAVA is the molarity analyte, volume analyte. MTVT means molarity titrant, volume titrant. Okay. And the reaction will be reversed if that's post-equivalence point. Okay. So this is how the equivalence equation is obtained. Okay. So we assume that these two systems will have the same potential. Okay. So we equate them together. And since the concentrations are also equivalent, we can just simply cancel out the log function, giving us this equation. Okay. But again, I will not dive into this I will not dive into these details anymore. What's Just use this equation, okay? But this is the derivation, okay? So this is how the equivalence point equation is derived anyway. Okay. So yeah. So this is the example here. I will not solve for the E cell this time because we have a very limited time. So we only meet 2 hours a week. So I'm not going to solve for this anyway. I will upload the answer on the worksheet, but I will give you an idea how to answer this. Okay. So again, I will not solve for the E cell, okay, or the voltage. I will just tell you the stages and how to use the equation. Okay. So for example, this is our problem. Calculate the cell potential when 50 ml of 0.1 molar Fe2 plus was titrated with 0.1 molar cerium 4 plus in a matrix of 1 molar hypochlorite. This is not hypochlorous. Perchloric acid. Okay. So in a matrix of 1 molar perchloric acid, the reaction is given as this, and the standard potential are written as this. Okay. So in any titration processes, you have to know the stages. Okay, so you have to know uh, what stage does this volume correspond to. Okay, so because depending on what stage you are in, there is a corresponding equation for that. Okay, so if you watch my lab videos on titration, acid-base titration, what I tell my students there is that they should know the stage first, because if you know the stage, then you will know the equation to be used. Okay, I don't know if that's the same thing as what your lab prof tells you, but again, knowing the stage is very important in any titration processes. So you should know first which stage are you in, then you apply the corresponding equations. Okay, so the first thing you have to do here is to solve for the equivalence point volume. Okay, so again, at equivalence point, we assume the mole analyte is equal to the mole titrant. Okay, so since our reaction has coefficients of 1, so we are not going to plug in anything. We are not going to plug things anymore. So just because the coefficient is just 1. Okay, so again, this is if you have a coefficient of 2, then that means you have to plug in 1/2 as the coefficient for the moles. Okay, so this is the thing that I have mistaken last time. No? So I'm sorry for that. No, so if you have a coefficient of 2, then what you're going to plug into this equation should be a fraction, not the whole number. So I explained the details in my post on Canvas naman. Okay. But I hope you got those things correct. And looking at your quiz scores, then I think you got it correctly naman. Okay. So yeah, you got high scores naman. Kaya I think we're good. Okay. So anyway, so again, if you have a coefficient of 2, instead of using 2, you use 1/2. Okay. I'm sorry for that again. I just overlook into that detail. Okay, so anyway, our coefficients are 1, so we assume that the mole of analyte is equal to the mole of the titrant. Okay, how do you solve for the moles? That's MAVA equals MT VT. So since we are solving for the volume of titrant at equivalence point, or the VTEP, that can be calculated as MAVA over MT. So what is the analyte here? So again, as a rule of thumb, the first species stated is the analyte, and the last thing to be mentioned is the titrant. Okay, and that's the rule of thumb here. So whatever is said first is your analyte, and what's next is the titrant. Okay. So iron 2 plus is our analyte here, and the titrant is cerium 4 plus. Okay, so plugging that, we get 50 times 0.1 divided by 0.1. So obviously, VTEP is 50 ml. So that's the volume of titrant at equivalence point. So since we know that 50 ml is our equivalence point, then that means these stages are pre-equivalence point, and these stages are post-equivalence point. Take note that for each stages, there is a corresponding equation. We use the Nernst for analyte here, and then here we use the Nernst for titrant. And for EP, we use the E system, which was derived earlier. So again, I will not answer this problem. I will not give you the answers for now. I will upload the answers in Canvas na lang. Okay. So just wait for that post. I will detail out the steps in solving for each volumes. Okay. I will show you there how to compute for each stages. Okay, I will use anyway. So these are the equation to be used in there. Okay, I just use this equation, in the plug the molarity of analyte, volume of analyte, molarity of titrant, volume of titrant, then you will get the E cell. Okay, so again, I wait for the file to be uploaded. I think I will upload it by Sunday. Okay, so I'll upload it by Sunday. Okay, so you can study on that. Or Saturday. Kasi Saturday is holiday. Okay, so maybe Saturday if I find time. Okay, so I'll upload the answers. So okay, so anyway, this is the answer. These are the answers, but the solving will be given to you by weekends. Okay, and I've also the same thing with this one. I will upload the answers by weekends. Okay, so you just wait for that file. Okay, so now we're done with any calculations. Let's now proceed with other um, with other top hindi, ano tawag doon? So we are now done with calculations. Let's proceed with concepts. Okay. So similar with acid-base titration, in redox titration, we sometimes need indicators. Okay. So remember, there are lots of indicators in the acid-base titration. So for example, your endpoint is at pH 8 to 10, then you can use phenolphthalein. Okay. If your endpoint is at pH 3 to 5, then you can use bromo cresol green. For redox titration, the pH doesn't matter. Okay, so that means we have to use other indicators. Okay, so these are some of the indicators in several redox titration methods. Okay, so for iodimetry, we use starch. No, when iodine reacts with starch, it produces a blue color. Okay, so once you see a blue color, then that means your titration is complete. Then you're done. Okay, so your titration is complete. For iodometry, the titrant is different. So this is sodium thiosulfate. I think that's sodium thiosulfate. Okay, and we also use starch indicator. So the transition anyway is blue to colorless. So once the color starts to fade, then that's the end of your titration. Okay, so you may ask, what's the difference of iodimetry and iodometry? So when we say iodimetry, this is used to measure, this is used to quantify reducing agents. For iodometry, this is for oxidizing agents. Okay? As of this point, I assume you know what is a reducing agent or what is an oxidizing agent. Reducing agents are those who underwent oxidation, and oxidizing agents are those who underwent reduction reactions. Okay, so the mnemonic I tell my students to use is Leora Geroa. Okay, so if you don't know this, this is losing electron oxidation reducing agent. So whoever's undergoes oxidation process is called reducing agent. Geroa, gaining electron reduction, and whoever undergoes reduction processes are called the oxidizing agents. Okay. So that's the mnemonic I tell my students to use. Okay. So if you're not familiar with this, then you can use this. Okay. Watch my lab video. Okay, because because I discussed this in depth to them. Okay. So anyway, so for permanganate method, the titrant to be used is potassium permanganate, which is pink colored. Okay. So we don't use any indicator for this because this is self-indicating. When you add enough permanganate ions, then the color will start to appear. Okay, so the color will start to appear when you add enough permanganate ion. So it will transition from colorless to purple. So when you have a pink color, then you stop. Okay, you stop titrating. Similar with phenolphthalein. When you start to see pink color, then you stop titrating. Okay. So the thing about permanganate, let me share you my experience with this, is that this is light sensitive. So that means when you are doing titrations using permanganate method, you should do this in darkness. Okay. So when I did it during my undergrad, no. So when we titrated chemicals with permanganates, no, we shut the lights, we shut the windows closed, then we turn off the lights. We only use dim light, okay? So we can monitor on the volume change or the color change. Because this chemical is very sensitive to light. It will start to degrade when exposed to light, okay? That's my experience with this one. This is a very fun titration because you are titrating in darkness, okay? So, yan. For dichromate, the titrant to be used is potassium dichromate and the indicator is diphenylamine. Similar with permanganate, it's the color transition is from colorless to purple. Okay. So by the way, dichromate is an orange colored powder. Okay. So this is colored orange. Mm. Okay. So other things to take note when doing redox titration is that you have to add auxiliary oxidizing or reducing agent before you start your titration. In acid-base titration, you just titrate right away, right? So as soon as you prepare your standard, you determine its standard concentration, then you can start titrating your analyte. But for redox reaction, you should add auxiliary agents first before you start titrating. Okay. So what are these auxiliary agents? These are used in analytes before titration to convert them into their desired forms. Okay. The problem with redox titration is that even air can influence the reaction. Okay, so even air can oxidize the chemicals in your in your container. Okay, so that means you really have to add auxiliary agents. Okay, so to prevent that from happening. Okay, so again, air is actually a good oxidizer. That's why our metals rust in the presence of air and water. Okay. So to prevent that from happening, we add these chemicals. If you want an if you want an auxiliary reducing agent, we use the Jones reductor or the Walden reductor. So these chemicals are used to reduce the metals, okay? The metal ion. So this is used to prevent them from oxidizing. Okay. So if you want auxiliary oxidizing agent, you use these chemicals, bismuthate, ammonium peroxide sulfate, and hydrogen peroxide. So again, why do we add auxiliary agents? Because air can actually react with our chemicals. Air can react with the chemicals. That's why you have to add this to prevent that from happening. Okay. So if you want to reduce your substances, use this. If you want to oxidize your substances, use this. Okay. Uh, Similar with acid-base titration, we have standard solutions, right? So for acids, we use HCl. That's the common acid titrant. For bases, the common one is the sodium hydroxide. Okay. In the redox titration, there are also preferred titrants. Okay. So the titrant for reducing agents are usually iron 2 sulfate, iron 2 solution or sodium thiosulfate solution. But for oxidizing titrants, we use potassium permanganate or cerium 4 solution. In the laboratory, the common one I used was potassium permanganate because cerium ion solution is quite expensive. Okay, but potassium permanganate is actually cheap. This is actually used in fireworks. Okay, so potassium permanganate is used as an oxidizer in fireworks. So this is relatively cheaper than this. So we use this instead of this. Okay. So again, these are the preferred titrants in redox titration. Okay. So similar with acid and base titration, there are preferred titrants and the preparation is the same as the previous ones. Okay. Okay, so we're done with redox. Now let's proceed with potentiometry. So the galvanic cell we described earlier is actually the basis of potentiometry. Okay, so this should be familiar to you because this was presented to you earlier in our lesson. Okay, so we know earlier that for galvanic cell, this thing on the left is called the anode, and this thing on the right is called the cathode. But for potentiometry, instead of calling this anode, we call it the reference electrode. And instead of calling this the cathode, we use this as the indicating electrode. Okay. So again, instead of using anode and cathode, we use reference electrode and indicating electrode. Okay. So depending on the cell potential or depending on the voltage of the cell here, you can determine the concentrations of the species you are measuring. Okay, so this is actually the basis for pH meter. Okay, so the potentiometry ones. So you have a reference electrode in the pH meter, and then you have the indicating electrode also in the pH meter. Okay, so this follows the Nernst equation. So meaning depending on the voltage, you can get the concentrations and vice versa. From the concentration, you can predict the voltage. Okay, so this is how the potentiometry titration looks like. Okay, so again, instead of calling it anode and cathode, we have the uh, reference and the indicating electrode. Okay. For example, here we have this reference electrode. I don't know what is this composed of because this is just arbitrary picture anyway. So they have this arbitrary electrode here, and on the other side you have the indicating electrode. So depending on the amount of ions in the solution, you can get the cell potential, and then from the cell potential you can use that to solve for the concentration of the species using the Nernst equation. Okay. So what are electrodes now? So electrodes are the thing you submerge into the solution. Okay. So those are the stuff you submerge in the solution. Okay. And they react with the solution to get the potential of the cell or the voltage of the cell. Okay. So reference electrodes, these are used as fixed potentials. So they are the reference of the study. Okay, so they give us the fixed potential, but the indicating electrode or the indicator electrode, this is the variable ones. Okay, so what the potentiometry does is that depending on the voltage the indicator electrode gives us, okay, it will compare the voltage of this with the reference. Okay, so by comparing the voltages, you can get the concentration. Okay. For reference electrodes, we have this two. So we have the primary standard electrode and the secondary standard electrode. Okay. So for primary standard electrode, the common electrode is the standard hydrogen electrode or the She. So this is called She, standard hydrogen electrode. Okay. So this is how it looks like. Okay, so a standard hydrogen electrode looks like this. So you have a gas supply of hydrogen, and then you have a platinum surface, and then you have your acid solution. So this is how the standard hydrogen electrode looks like. So what's the purpose of platinum? The purpose of platinum is to provide surface area for the gas to react with. Without platinum, the reaction is not possible. Okay. So this provides surface area for the gas to react with. Also, this can be connected with the anode. Okay, so I mean with the indicating electrode. This can be connected with the indicating electrode. You can connect this using wire M. Okay, so that's the primary standard electrode, the She or the standard electrode. The secondary standard electrode uses other electrodes, no, such as the calomel electrode. So basically what you have here is that you have, instead of having this setup, you have this setup in here. So this is how the standard Calomel and the AgAgCl electrode looks like. Basically, for standard Calomel, it uses mercury as an electrode. For AgAgCl, it uses silver as your electrode. Okay. So standard Calomel electrode is actually an old electrode. This is old. This is a relatively older electrode than everything else. Okay, so that's why it uses mercury. But uh, since we do not really want to use mercury in the lab, we use this one instead. Okay, because mercury is toxic. No? So we really don't use this too much. Okay. So for indicating electrodes, there are three kinds of electrodes. You have the metal indicator, membrane electrodes, and the ion selective electrodes. Okay. So the name itself suggests that the metal indicators are used to determine metal ions. Okay. For membrane electrodes, these are used to determine the P values, okay, such as the pH, the P calcium, or the P nitrate. Okay. And then for ion selective electrodes, these are used to determine the concentration of specific ions. Okay. So let's talk about the metal indicator first. So we have the first kind electrodes. When we say first kind electrodes, basically your electrode is just a metal surface. Okay. So you will just dip a metal onto it. So that's the first kind electrode. For second kind electrode, what you need to do is that your metal has to be coated with a precipitate. Okay? For example, my metal is silver. If I coat it with silver chloride, then it is now called a second kind electrode. Okay? So you just add a coat of precipitate. The third kind electrodes are the inert electrodes, commonly platinum electrodes. Okay? So yeah, inert electrodes or platinum electrodes. Those are the common ones. This is Ag and AgCl. Okay. For metal, let's say that's just Ag. Okay. So these are some examples. But for inert electrodes, the commonly used one is the platinum. Okay. For membrane electrodes, we use glass. No, we use glass electrodes here. Okay, so we use glass electrodes. No? That's why the pH meter has this glass bulb at the bottom. Okay, so if you are familiar with pH meters, if you look at the bottom part of the electrode, you can see a glass there. So your teacher usually tells you to be careful when handling that glass because that glass is a membrane electrode. Okay, it is very sensitive. So that's why you are not supposed to touch it. Okay, you can only rinse it, but no touching. Okay, so glass electrodes are very sensitive. It may break. Okay, so please be careful when handling pH meters. So it is used to determine the pH values or the P values. P calcium, this is quite unfamiliar for you, no? But this is used to determine the hardness of the water. So this is used to determine the water hardness. For example, if you work with Maynilad or uh, Manila Water, okay, so Maynilad and Manila Water are our water subsidiary in the Philippines, okay? So if you want to determine the calcium content of your water, then you need to use a PCA meter, not the pH meter. So it works with same concept pa rin naman, okay? So you just submerge an electrode, then it will determine the calcium content of your solution. Okay. So the higher the calcium content is, the hard the water is. Okay. So in water supply, we try to minimize the amount of calcium in our water system because what happens when you have calcium in your water, it precipitates out. Okay. So that's why in the province, no, if you have a well water, if you boil off the water, what happens inside your kettle? there are white precipitates in there. The white precipitates in the kettle when you boil off the water is the calcium. Those are calcium deposits. Okay. So we don't want that in our pipelines, because if calcium deposits on water pipelines, then chances are those pipelines will be destroyed anytime soon. Okay. So when those calcium builds up in the joints, then that's very uh, dangerous. Okay, because it is a potential risk. Okay? So the pipe may explode when we have too much calcium in the water. Okay, so this is used by water providers, such as Maynilad and Manila Water. P nitrate, this is used by agriculturists to determine the amount of nitrate in the soil. So basically, that is just an electrode. You plug it into the soil, directly into the soil, or you get a soil sample, you add water, and then you plug in nitrate the nitrate meter. Okay. So depending on the amount of nitrates, then you can tell whether the soil is fertile or not. No? Depending on the nitrate solution, excuse me, the nitrate ions in the soil, then your soil may be fertile or not. No? The higher the nitrate is, that means the more fertile it is. No? Because remember, um, nitrates are needed by plants for nitrogen fixation. Okay, remember that in your LM days, in your elementary days, we know that nitrogen fixation is used by plants to produce legumes. No, okay, legumes or beans. No, so yan. So nitrates are very important in in nitrogen fixation. Okay. So for ion selective electrodes, so these are any ions other than these ions here. Okay. For example, you can use um, lead electrode to determine lead ion. Okay. So this is actually the thesis of one of the chemistry board examiner in the Philippines. Okay. So her thesis, that was Ma'am Adoracion Resurrection. She works at PNRI, so I actually had an opportunity to talk with her because my OJT was in PNRI, Philippine Nuclear Research Industry. Okay. Institute rather. Okay. So I had the chance to talk with her about her thesis, and she told me that this was her thesis now. So her thesis was she created an ion selective electrode which can measure the amount of lead in the air. Okay, take note, in the air, not in the solution. Okay, so that is a very technical thesis, but yeah, she was able to do that. And then lastly, we have voltammetry. So earlier, we used cell potential to measure the concentration of our species, right? But for voltammetry, instead of using cell potential, we use the current. Okay. So we use the current. So are the current and the cell potential related? Yes. No. According to physics, the cell potential is the product of the current and the resistance, diba? So instead of using voltage, we use current. Now, we measure current in voltammetry. Okay. So, yeah. So, by changing the current, we can create what's called the voltammogram. Okay. So, that is the graph that is produced in voltammetry. And unlike potentiometry, wherein the graph is like this now. So, in potentiometry, the graph look like this. In voltammetry, since we are using current or amperes, the graph looks different. Okay, so one graph actually looks like this. Okay, so it is quite circular. So let me show you an example. Voltammogram. To show you an example of the voltammogram. Okay, so again, for potentiometry, the graph looks like an acid-base titration. But for voltammetry, this is how the graph will look like. Okay, so it is very different with the ones we just discussed earlier. Okay, so yeah, so this is how it looks like. Sometimes it looks like this, sometimes it looks like this. Okay, so the graph is very different with the potentiometry. Okay, so that means voltammetry is a very different topic. It has a very different approach compared to potentiometry. Anyway, so voltammetry makes use of three electrodes in order for this to work. You have a working electrode, reference electrode, and the auxiliary electrode. Okay, so this is how the setup looks like. So suppose you have a solution here. Three electrodes has to be submerged into that. Okay. Okay, so you have to submerge all these three electrodes for that to work. Okay. So working electrodes are commonly mercury electrodes. Okay. So these are commonly mercury electrodes or platinum electrodes. For reference electrodes, these are the reference, just like in the standard hydrogen electrode. Okay. So the common electrode here is the calomel and the AgAgCl, which we know as the secondary reference electrodes in potentiometry. They are still used in voltammetry. Then for auxiliary electrode, this is just an electrode used to measure the current. No, this is used to measure the current. And then the working electrode, this is the one that changes the voltage of the solution. Okay. So anyway, so these are the types of voltammetry. We're not going to go into deeper details because again, voltammetry is a very quite different concept now compared with potentiometry. So if you're a BS chemistry student, then we will discuss it. But since you're not, then we'll just go past it. Okay. So this is one example of the voltammetry. So on this one, you have a polarography. Oops, I'm sorry. Okay. So this is polarography. So as you can see here, this is how the voltammetry looks like. Okay, so you have to have three electrodes submerged into a solution. So one of them is the working, the other is the reference, and then the other is auxiliary. Take note that the auxiliary will measure the current changes or the changes in the amperes of the solution. Okay. By measuring those properties, we will get graphs that look like this. Okay, it looks like a duck. That's why sometimes they call it the duck curve. Okay, and the duck curve. Sometimes the graph looks like this. Okay, and sometimes they look like this. Anyway, so with that, we're done with chapter 6 now. I hope that you learned something today. Anyway, I'd like to emphasize on some things. Um, for the quiz in this topic, so we will only have one quiz, okay? So we will only have one quiz. I will open that by next week, okay? So we will have one quiz for this topic only. So that means it has 20 items. In those 20 items, majority of it will be concept or terms, okay? So basically the concepts here and the terms here. And then the minority of topics, I can't give an exact number because I'm not yet done making the quiz, okay? So, but the majority of the questions will be concepts, okay? So read carefully the details in the PowerPoint, okay? And also study electrochem and electrochemical cells in your laboratory, okay? So I hope this was discussed already. Okay. The minority of topics will be calculations. And for calculations, um, it will cover E-cell calculation, cell potential calculation, the use of Nernst equation, and then the titration calculations. Again, for the calculation part, I will be uploading worksheet on Canvas by the weekend. Okay. So for you to be guided with the calculation. But again, as you wait for that worksheet, I want you to try solving for this one, huh? So I want you to try solving for this one because I already gave the answers. All you have to do is to just plug in the equations. Plug in the concentration of the molarity of analyte, molarity titrant, volume analyte. So just plug them in here, okay? So you can get the E cell, okay? Okay. But again, I will give you the solution to these problems by the weekends, okay? So just wait for the file or just wait for the announcement that the file has been uploaded, okay? So again, so thank you for attending our class. If you have questions, please don't hesitate to ask me, even if that's laboratory topic, okay? So if you want to watch my lab lessons, you can go to our YouTube channel, which just surpassed 1K subscribers. So yeah, this is a small achievement for me. Anyway, so yeah, so you can watch those videos, huh? Okay. By the way, let's go to our canvas muna and let's clarify some things here. I made an announcement last time, right, about the schedule of our classes. So thank you. So I was actually able to monetize the videos na, no? But but my classes for this semester, I'm not going to monetize those video. Of course, I'm being paid. I'm being paid by the university for this semester. By the way, my plan for that YouTube account is since you have qualifying exam next year, so I will be preparing videos, uh, review videos of chemistry. Okay, so I will be preparing review videos in chemistry by June, July. Okay, so you can use those videos when you are about to take the qualifying exam next year. Okay, so I hope that will help you in chemistry. Okay, okay, so I will discuss analytical chem there again, but in shorter video clips, maybe around 10 minutes. Okay, then I will also discuss inorganic chemistry and organic chem. Okay, so I hope that project, no, that will be my project for June, July. So I hope that will help you for your qualifying exams. No? So hopefully, nakatulong. So next year pa naman kayo. No? You will take your qualifying exam by next year pa. But it is better if we can do it, if we can review as early as now. No? So I hope you will, you will watch those videos. No? Because those videos are intended for you. Okay? Okay. So anyway, let's go through some announcements here. Again, regarding about quiz 5, yeah, about quiz 5, the answers have been posted on Canvas na, no? But I will upload the calculations, okay? So I will upload the detailed calculation for each questions, okay? For you to review, okay? So I will upload them. If your answers are close to the correct answer, then I will consider them, okay? I will consider them. Suppose, for example, your answer is off by a decimal, then I can accept that. No? However, the adjustment will be made by Saturday. Okay? I will make adjustments by Saturday because I have classes today. And also, important dates to remember. We are now here, so we're done with chapter 6, right? Okay, so I will upload the quiz by Saturday together with the worksheet. Okay. So this will be open for few days, no? So just few days lang. Yeah. Okay. So anyway, so this quiz will be open for a few days lang. Okay. So unlike the quiz 5, because quiz 5 is a very long topic. So but for quiz 6, we can do it in 3 days lang. So again, I will upload the worksheet. No? So I hope that will be useful when you review for this quiz. And then next week will be our last synchronous meeting. So this will be the last time you will see me because I will not be teaching biochem next year. Okay. I'm not going to teach biochem. So my field of expertise involves inorganic chem, org chem, and anachem lang. But for biochem, other professors love that subject, so we let them to handle those subjects. Okay, so this will be the last day that we will meet. Okay, however, we will still have discussion for chapter 8, no? But this will be asynchronous anyway. So I will upload the video for chapter 8 on Sunday, May 9, so you can study them in advance. And I will upload the quiz in advance as well. And this will be your finals week, okay? So that means after this, you will get your grades na. So take note of the dates, huh? So again, May 7 will be our last synchronous sessions. So this will be the last time we will meet. And for chapter 8, this will be asynchronous. So I will upload it by May 9. Okay. So you can study it in advance. I'm planning not to have any synchronous classes anymore a week before the finals. So you can review. Okay. Then you will have your finals week in Anachem. Your grades will be uploaded in your central accounts by um, May 24 to 26, but I am planning to upload them as early as 24 or 25 na. You will see your grades after this encoding dates. So maybe May 27, you can see your grades. Um, I will be sending you a grade computation for transparency. Okay. So although that is not required by the university, the only required thing is the midterm consultation. But for the finals, we are not required to give details about your grades. But for me, for transparency purposes, I will be sending you your grades calculation. Okay, so I will do that for personal reasons. No? So I just want to be I just want to be clear on why you got this grade na bakit ganito grade ko. So yan. But again, don't expect other professors to do that now because again that is not required. No. I will just do that because I want to do that. Okay. So that will be all. Okay. So those are yun lang. Okay. So again, next week will be our last synchronous meeting. So I hope you learned something from me. And even though we have a very rough times, especially in the second semester. Okay. So I'll see you again next time. Okay. So for now, we're good to go. Okay. So thank you for attending our session for today. A copy of the video will be uploaded on YouTube. Okay. Thank you, and I'll see you again.